This video, we will look at asymptotes. An asymptote will be values for x where the function is undefined, or values for x where the graph does not touch. Now, the graph will approach these values, but it will never touch or cross these values. So there are three types of asymptotes. One is your vertical asymptotes, two, horizontal asymptotes, three would be your oblique or slant asymptotes. So let's look at the first type, vertical asymptotes. So there'll be values for x where the denominator is 0, or in other words, values for x where your rational expression is undefined. So if we want to find the vertical asymptote of f of x equal to x over x squared minus 9, what I would do first is set x squared minus 9 equal to 0. I decided to solve by factoring using the difference of squares. X squared minus 9 is equal to x plus 3 times x minus 3. Now set each piece equal to 0. X plus 3 equal to 0 will give you x equal to negative 3. X minus 3 equal to 0 will give you x equal to 3. Both of those are vertical asymptotes. So here we have a rough sketch of how the graph would look. We have this imaginary line of x equal to negative 3, imaginary line of x equal to 3. On the left side of x equal to negative 3, you see the graph does approach it. And the same thing happens on the right side, but it never crosses or touches it. Looking at x equal to 3, the graph approaches it on the left side and approaches it on the right side, but never crosses or touches. Look at another one. So if I had g of x equal to x plus 3 over x squared minus 9. So if you can factor and reduce your function, you are expected to do so. So the bottom I factored into x plus 3 times x minus 3. Notice the x plus 3 cancels in the top and bottom, leaving me 1 over x minus 3. So from there, I can establish my vertical asymptote by setting my denominator equal to 0. X minus 3 equal to 0 would leave me with just x equal to 3. But I cannot forget how my function was set up in its original state. X plus 3 was in my denominator, so I have to give an account for that. Set that equal to 0, that gives me x equal to negative 3. So what that means is that I have a vertical asymptote at x equal to 3 and a restricted value at x equal to negative 3. So the graph doesn't exist in either point. It's just that I would have a vertical asymptote at that x equal to 3, and then I would have an open circle at x equal to negative 3. Last one, dealing with vertical asymptotes. If I have x plus 3 over x squared plus 9, I follow the same procedures. Take x plus 9, set it equal to 0, try to solve. Once I do that, I will recognize that my solutions that I would get would be imaginary, since I would not get any real solutions from the setting of the denominator equal to 0. That means I would have no vertical asymptotes. Proceed. Second type, horizontal asymptotes. If I decide to let n be equal to the degree of the numerator, or in other words, the highest exponent of the numerator, and let m be the degree of the denominator, highest exponent in your denominator, if n is less than m, my horizontal asymptote will be y equal to 0. If n is equal to m, I will take the leading coefficient from both top and bottom and divide them, and that will be my horizontal asymptote. And then if n is greater than m, there is no horizontal asymptote. So let's take that and apply it. If f of x is equal to 4x over 2x squared plus 1, don't forget, if you don't see an exponent, they assume you know there's a 1 there. So that means n is equal to 1, m is equal to 2. Since n is less than m, that means my horizontal asymptote is y equals 0. For the next one, I have 4x squared over 2x squared plus 1. Both of my exponents of my numerator and denominator are equal. In other words, both of my degrees, I shouldn't have said exponents, both of the degrees of my numerator and denominator are both equal to 2. Since they are equal, I take the coefficient, the leading coefficient of both numerator and denominator. That would be 4 and 2. 4 divided by 2 will equal to 2. So that means the horizontal asymptote for g of x will be y equal to 2. Then for the final one, dealing with horizontal asymptotes, my degree of my numerator would be 3. The degree of my denominator would be 2. Since n is greater than m, there is no horizontal asymptote. Final one, slant asymptotes. If the degree of the numerator is greater than the degree of the denominator, then the graph has a slant asymptote. So if I want to find a slant asymptote of x squared minus 4x minus 5 over x minus 3, I recognize that the degree of my numerator is 2, degree of my denominator is 1. So I go ahead and divide. I can use long division or synthetic division if the setup allows. I decided to use synthetic division in this case. If I do decide to do so, don't forget if I have x minus 3, then what goes in my partial box over here is the positive 3. It's always the opposite sign. And then I use my coefficients, 1, -4, -5. Bring down 1, 3 times 1 is 3. Add these together, it's -1. 3 times -1 is -3. Add these together, it's -8, which will be my remainder. So the setup of my answer, you always started with 1 degree less than what you originally had. That's x minus 1 minus 8 over x minus 3. That's what I was dividing by. So the quotient part, this is my quotient, x minus 1. That's my slant asymptote. I put y in front of that. Y is equal to x minus 1. The remainder has nothing to do with your slant asymptote. The part that comes before the remainder, your quotient, will be your slant asymptote. Also, just a side note, I have a vertical asymptote here. When I take x minus 3 set it equal to 0, solve it, I will have a vertical asymptote at x equal to 3. So that's how you find your slant asymptotes. Also, keep in mind that when I'm looking at my vertical asymptotes, it's going to start off with x equals. But my horizontal asymptote and my slant asymptote start solving with y equals. All right, let me know if you have any questions.